Yes. Good evening, everyone. Welcome to the problem solving session of NPTEL Thermodynamics course. I am one of the TA of the course. Myself, Pradeev E. I am a second year PhD student in the IIT Madras. I work in the Department of Mechanical Engineering. So I hope my screen is visible to everyone. If not, you can comment in the chat box. I hope you have gone through the first week videos. Now I will solve some problems which are relevant to those lectures. So first problem for today is here. A pump discharges a liquid into a drum at a rate of 0.0032 meter cube per second. The drum is of 1.5 meter diameter and 4.2 meters in length, and it can hold a liquid of 3000 kg. So we need to find the density of the liquid and mass flow rate of the liquid handled by the pump. So we have given a volume flow rate, we have given the volume of the container and also the mass of the fluid that the container can hold, and we need to find the density and mass flow rate. So first we can start with calculating the volume of the container. So to calculate the volume, we have pi by 4 d square into h. So this is given by pi by 4 into 1.5 square into 4.2. So I hope you have the calculators ready with you. So this turns out to be 7.42 meter cube. Now we can calculate the density. So we have the mass of the fluid as liquid as 3000 kg, and we have volume as 7.42. Can someone put in the chat box how I can calculate the density? Density is generally represented by the Greek alphabet rho, that is given by mass by volume. So mass here is 3000 divided by 7.42. We have 404.31 kg per meter cube. So we have calculated the density, and next we can calculate the volume flow rate. So for volume flow rate, we have we have to calculate the mass flow rate. So volume flow rate is given by assume V dot is equal to 0.0032 meter cube per second, and we have density as 404.3. So if you want to calculate m dot, this is given by V dot into O. So we have 0.0032 into rho is 404.3, which is 1.294 kg per second. anyone have some doubts in this? Sorry about my bad handwriting. I had a different touch display which was not working in the last moment, so I got a different display where I have to write with my finger. So I hope from next time we will sort this issue and it will be better. So if you have any doubts in this problem, you can ask, or you can move to the next one. Okay. Moving on to the next one. We need to convert some of the pressure readings to kilopascals, assuming a barometer reading of 760 mm Hg. So a barometer, I hope you would have known about barometer. So 760 mm of Hg means, so assume we have a barometer like this. This is open to atmosphere. This is open to atmosphere, and here this is filled with mercury, and this length is 760 mm. So here there will be vacuum inside the on the top of the mercury filling column, and 760 mm of mercury means if you want to calculate the atmospheric pressure PATM, we have rho GH. So at this point, at the bottom of the mercury column, the force acting is given by the mass of the column into acceleration due to gravity, so which will be m into g, and then we have pressure which is given by force by area. So putting all this together, we get density into acceleration due to gravity into this height, column height h. So now we have PATM, or atmospheric pressure, to be rho GH, and rho for mercury is 36,600, and acceleration due to gravity we can take it as 9.81 unless otherwise stated, and then we have h to be 760 mm. So we need to have all units in SI units. So 760 mm is 0.76 meters. So we have 101,396 Pascal. So putting this in kilopascal, we can write 101.4 kilopascal. So this is the atmospheric pressure, and now we can go to the problem and convert the given gauge pressure or vacuum pressure to in terms of kilopascal. I hope this section of the problem is clear. If not, you are free to ask me questions. So moving to the first one, 90 mm of mercury. So the total pressure is given by PATM atmospheric plus rho GH. So now the rho GH is again 13. So this PATM can be given by 1.1.4 into 10 power 3, writing in Pascal, and then we have rho GH. Rho GH is 13,600 into 9.81 into height is 90 centimeters. So this is centimeters. So we have 0.9 meters. So adding this up, we get 221.47 221.47 into 10 power 3 pascals. So this can be written as 221 kilopascal. So we know the atmospheric pressure using a manometer or a barometer, and so based on the barometric reading we get the atmospheric pressure, and now we measure a gauge pressure that is over the atmosphere, and that is given as 90 centimeters. So the total pressure is given by the atmospheric pressure plus the gauge pressure. So atmospheric pressure is P80 we have calculated earlier, and now the gauge pressure is rho gh, and we have substituted the density G and H values, and we have got the absolute pressure for 90 centimeter mercury gauge pressure. Next we have 40 centimeters mercury vacuum. So for this we have total pressure as P. Total pressure P is given by P ATM, atmospheric pressure, minus the vacuum pressure. Now again it is given by rho GH. So here rho GH, sorry, P ATM is 101.4 into 10 power 3 pascals, plus rho is 13,600 into acceleration due to gravity, into height is 40 centimeters, so that is given by 0.4. So this should be subtracted with the atmospheric pressure, so this should be a negative sign here. Now this turns out to be 48 into 10 power 3 pascals, which is 48 kilopascal. So now, so this is the absolute pressure. 48 kilopascal is the absolute pressure, whereas 101.4 is 101.4 kilopascal is atmospheric pressure. Since the meter is really in a vacuum, we have subtracted it from the atmospheric pressure, and we have got 48 kilopascal as absolute pressure. I hope this is clear. Now the third problem is we have 1.2 meters of water gauge pressure. 1.2 meters H2O gauge. Again we write P is equal to P atmospheric plus rho GH. Now atmospheric is 101.4 into 10 power 3 plus gauge, sorry, rho GH is, since it is water, the density is 1000 into acceleration due to gravity 9.81 into height is 1.2 meters. So adding this up together we get 113.17 into 10 power 3 pascals, which is 113.17 kilopascal. The last subsection of the problem is fairly simple. So this one is 3.1 bar. So that means bar is 10 power 5 pascal. So right here bar is 10 power 5 pascals. So we can convert, if we convert it will become 310 kilopascals, which I think you can easily work out. the next problem. If you have any doubts, you can raise your hands or put in the chat box. Okay, Anand Gupta, P is equal to rho GH, P absolute is equal to rho G plus P absolute is rho GH plus P atmospheric. So now the next problem, we have a 30-meter high vertical column of fluid of density 1878 kg per meter cube in a place where the acceleration due to gravity is 9.65. Now we need to calculate the pressure at the base of the column, fluid column. So again, so this pressure is given by rho GH. Rho is 1878 into G is 9.65. So since the G is specifically given, we take the G value that is given, otherwise we take 9.81. And now we have H to be 30 meters. So this pressure is be roughly 544 into 10 power 3 pascals. Converting to kilopascal, it will become 544 kilopascal. Anyone have any doubt? Moving on to the next problem, we have the pressure of steam flowing in a pipeline, which is measured using a mercury manometer as given in the figure. Some steam condenses into water in the column, and we need to estimate the steam pressure in kilopascals. So we can take the density of the mercury to be 13.6 into 10 power 3 kg per meter cube, that is 13,600, and density of water to be 10,000, and the barometer reading is given as 76.1 centimeters of mercury, and acceleration due to gravity is given as 9.806 meter per second square. So now we have this manometer. The steam is flowing this way, and steam is flowing with a certain pressure P, and this pressure is exerted on the fluid here, and because of this the fluid displaces and moves up. On the other limb it moves up. The other limb is subjected to P naught, which represents P atmosphere. So that is given by 76.1 centimeters of mercury. So for generally it is mercury manometer, but because of some steam condensed, some H2O or steam or water of 3 centimeters of the column is can be observed, and the mercury level is from this mercury to this mercury is 50 centimeters. So that is given. Now we can, I think we should start solving by calculating the atmospheric pressure. So P atmosphere is equal to rho GH. So that is 13,600 into 9.806 into height is 0.761 meters. So this is 101.48. So I will round it off to 101.5 into 10 power 3 pascals, or it is 101.5 kilopascal. Now we take this point as datum or a reference point, So below this we have only the same fluid mercury, and above this we have on the both limbs we have different fluids. So on the left hand limb we have water for 3 centimeters, and then we have steam pressure acting on the water column, and on the right limb we have only mercury acting, mercury of 50 centimeters column acting on it on this datum, and then we have atmospheric pressure subjected to the right hand limb. So at equilibrium these two pressures should be equal. The pressure from the datum point on the left hand limb should be equal to the pressure on the right hand limb. So we can equating that, I write pressure on left hand limb is equal to pressure on right hand limb, and pressure on the left hand limb is given by two elements. So one is the steam pressure and then the water column pressure due to water column. Steam pressure we take it as P, and then for the water column we have rho GH, which is since it is water we take rho to be 1000, and G is given as 9.806, and rho GH is 3 centimeters, so which is 0.03 meters. And on the right hand side we have P atmospheric pressure plus rho GH for mercury, which is 13,600 for rho, and G is given by 9.806, and H is 50 centimeters, which is 0.5 meters. Here we know P atmosphere to be 101.5 kilopascal, or 101 into 10 power 3. So every time we should ensure that we use with all the SI units. So even if we know in kilopascal, we should convert to pascals. Now we can calculate pressure. P is equal to put in all the terms on the right hand side. We will have 101.5 into 10 power 3 plus the pressure due to the mercury column is 13,600 into 9.806 into 0.5, so that is 66.7 into 10 power 3, and then we need to subtract the water column because it was on the left hand side, left limb. So that is 1000 into 9.806 into 0.03. So we get 294.18. So finally, the pressure we have 167.8 into 10 power 3 pascals, which is 167.8 kilopascal. If you have any doubts in this problem, you can put in the chat box. Okay, moving on to the next problem. We have a vacuum gauge mounted on a condenser which reads 0.66 meters of mercury. What is the absolute pressure in the condenser in kilopascals when the atmospheric pressure is 101.3 kilopascal? So now we need to calculate the absolute pressure given by P, which is equal to P atmospheric minus P vacuum. So this P vacuum is given by rho GH, where rho represents density of mercury, G is atmospheric acceleration due to gravity, and H is 0.66 meters. So atmospheric pressure is given as 101.3 kilopascal. So converting to pascals, we have into 10 power 3 minus rho GH. Rho GH is 13,600 into 9.8 into 0.66 meters. So this is 13.24 into 10 power 3 pascals, or 13.24 kilopascal. But I think in the book it is given as 8.8 kilopascal. If you are getting a different answer than mine, you can always stop me in chat box. Okay. So far the problems, the previous problems were taken from PK book. This problem, the next two problems are taken from Senjo. So here we have a manometer attached to a pipe, as shown in the figure. The pipe has an air at 76 kilopascal as absolute pressure. The specific gravity of one liquid is given to be 13.55, and we need to find the specific gravity at the other side. So specific gravity of the second fluid. So first fluid is from here to this point, and the second fluid is from here to this point. So we can take this as datum, and then so that the below the datum is the same fluid, and to be in equilibrium, the pressure above this datum point should match on both left hand side and the right hand side. So writing the equations, we have pressure on left hand side equal to pressure on right hand side. Pressure on left can be given by first P air plus rho 1 G H1. So rho 1 represents fluid with specific gravity of 13.55, and then height is given by 22 centimeters, and then this should be equal to P atmosphere plus rho 2 G H2. So to calculate density rho from specific gravity, we need to multiply by the density of water. So generally specific gravity is defined as density of the fluid by density of water. So if you want to calculate density of the fluid, we have specific gravity into 1000, so or the density of water. So now we can substitute the values in this equation and solve. So P air is 76 into 10 power 3 pascals plus rho 1 is 13.15 into 1000, 13.55 into 1000, so that becomes 13,550, and G is not given, so we can take 9.8, and H is given to be 22 centimeters, which is 0.22 meters. This should be equal to atmospheric pressure, which is given to be 100 kilopascals, and plus we have rho 2, which we can find, and G is 9.8, and height of the column is 0.4 meters. So solving this, we have rho 2 is equal to 76 into 10 power 3 plus multiplying 13,550 into 9.8 into 0.22 gives 29 29 point sorry 29.2 into 10 power 3 minus 100 into 10 power 3 the whole divided by 9.8 into 0.4. So this is 1336 kg per meter cube. So now to calculate the specific gravity, we have rho 2 by rho of water, that is 1000. So it should be 1.3 1.336. Again, if you have any questions, you can ask. Otherwise, I can go to the next problem. Okay. Next problem is we have to consider a system as shown in the figure. So we can see that we have two limbs of different size. Left hand limb has a cross-sectional area of A1, and on the right hand side of the limb has a cross-section area of A2. The right hand side of the limb is connected to a brine pipe whose specific gravity is given to be 1.1. The manometer has a manometric fluid of mercury with specific gravity 13.56 at the bottom, and on the right hand lip this mercury is directly subjected to the brine pipe. At the left hand limb, this mercury column is column has water on top of it for certain height, and then it is subjected to air. Now it is given that when there is a 0.7 kilopascal change in the change in pressure of the air, we see a drop of 5 mm in the brine level in the right column. I hope the problem is clear. So now we need to find the ratio between A2 and A1. Okay. So when there is a 0.7 kilopascal of change in the air pressure, the brine level goes down by 5 mm, and with this we can calculate the ratio of A2 by A1. So initially when there is no change in the air pressure, we take this to be the datum, and we say this height as h3, this as from the datum, this height as h1, and water height as h2. Now from the datum, if we start equalizing the pressure on the left hand side, on the right hand side, we can write on the left we will have first P air plus rho 1 G H1. So this represents the pressure caused by the mercury column of height h1, and plus we have row 2 g h2. This is the water column of height h2. This should be equal to pressure in the brine pipe given by PB plus rho GH of this brine column. So that is rho 2 G, rho 3 GH3. So 3 represents the brine solution, 1 represents mercury, and 2 represents water. So this we can take it as equation 1. In the second state, where the pressure is changed by, or pressure is reduced by 0.7 kilopascal, we take that condition a second. So when the pressure is increasing, we see they have told that the brine column goes down by 5 mm. So there will be a new datum here. There will be a new datum. So this can be given as, so this H2 will remain same. It will not change. This H1 will become, I will write H1 prime for the new condition. It will be H1 minus X minus 5. This X is the fluid column that is falling from this one. Because from the left hand column, some fluid goes to the right hand column. So because of this, some H1 drops to some value, and this 5 into 10 power minus 3, this is in 5 mm. So since the datum is changing, this will again fall by, so we will take a new datum which will be 5 mm, which will make the H1 prime as lower by another 5 mm. So now this X can be calculated by equating the volume which has dropped on the left column should be equal to the volume which is gained on the right column. So that is A1 into X is equal to A2 into 5 mm. So this is into 5. So H1 prime is H1 minus X into minus 5 E minus 3, and H2 prime is given by H2 minus 5 into 10 power minus 3, just because we are taking a datum, this is H3. We are taking a datum which will reduce this column by 5 mm. So now we can write a new equation, PA minus 70 into 10 power minus 3 into 10 power 3, because the drop in pressure is 70 kilopascal, plus rho 1 GH1, so that will become rho 1 G H1 prime, which is H1 minus X minus 5 into 10 power minus 3, and we have the water column which is the same, plus rho 2 GH2, which is equal to P prime, which also remains unchanged, plus we have rho 3 GH3 H3 prime, which is now H3 minus 5 into 10 power minus 3. So this we can take it as equation 2. So when we have equation 2 minus equation 1, the P atmosphere will go, when we have equation 1 minus 2, P atmosphere will be the same, rho 2g H2 term will be the same, so it will get cancelled out. PB will get cancelled out because then it is same, and here this H1 rho g H1 part H1 will go off, and then similarly on the right hand side we have rho g H3, this H3 will also get cancelled. So we have these terms remaining, and when we solve for when we solve for this, we will be getting x to be, we can solve for x will become 6.67 into 10 power minus 4. So this is in meters, so we had a1 into x equal to a2 into 5 into 10 power minus 3. So a2 by a1 will become 1.33 into 10 power minus 4. Do you have any questions? If you have any questions, you can also put in the discussion forum, and this video will also be available in YouTube, and the link will also be shared with you later. And I will also upload this lecture notes, and it will be the link will also be given to you. So these are the questions I had for today. If you have any questions, you can ask, we can discuss. If you have any questions in this problems, or if you have in the lectures also, you can ask, since we have some 15 minutes left. Otherwise we can close the class. Okay then, thank you for attending the class. I will end the class now. We will see, we will meet again in the next Friday at 6 p.m. Yes, yes Bhavesh, I will, I don't know if it will be coming by mail. I will give to NPTEL team, and they will either upload in the portal, or they will send you a link to this PDF. If possible, I will also write using a different pen properly, and then I will upload.
Thank you, sir. Thank you.
Thank you.